Okay, so let's get started. We'll continue our journey through automatic repeat request protocols, retransmission protocols. And the whole reason to study this is to fix a nice service for the upper layers, while a service which is below us is not very good. So, okay, so ARQ stands for Automatic Repeat Request. It's an old name. It comes from way back, so it has no real good interpretation right nowadays, except it's always called ARQ. It's retransmission protocols. And the purpose is to deliver a service that delivers packets in order, without errors and without duplications. So if I'm implementing this protocol, I accept service data units from the layer above it. And what I want to guarantee to the layer above me is that I will guarantee to transmit your service data units to the other side without errors and without duplications and in order. Okay. While the layer below me makes no such guarantees. The layer below me just say, I will send you packets. Maybe go through, maybe not. I guarantee nothing. Right? So the basic elements of such a protocol here, in order to clean up the service, which is pretty bad below me, to something which is pretty nice above me, is to use a few things. We need error detecting codes, and we need fairly good ones. So we'll be able to, at the receiving side, figure out whether a received frame is in error or not. We need sequence numbers in order to keep track on in which order to deliver the packets at the receiving end. We need acknowledgements, which is receipts of a successful received frame, which is transmitted from the receiver to the transmitter. Okay. Sometimes we need some special types of acknowledgements, which are called negative acknowledgements, which basically says, I saw a frame here which I don't think is in the right order. Could you please send the right one instead? Okay. And we need timeouts. And timeouts is because when I send a packet, it's on its way. It may never arrive. Right? So after a while, I give up on that and I try again. So we need some type of timeout mechanism. Okay. And we saw last time that without sequence numbers and without these without sequence numbers, lost acknowledgements or premature timeouts, which a premature timeout is when I transmit the packet too quickly. I'm getting nervous about the packet. I just keep on transmitting packets. Then this might cause lost packets and or duplicate packets. Okay, so we need all these things, right? And then we talked about one basic protocol for doing this. And that's called stop and wait. It's the easiest protocol, and it's quite easy. Simply, I get a data unit, service data unit from above. My task is to make sure that it's delivered. So I take one, and I send it, and then wait for an acknowledgement from the other side. If I get an acknowledgement, I take another packet and transmit. If I don't get an acknowledgement, I assume something gone wrong, and I retransmit this packet again, wait until I get an acknowledgement. If I don't get an acknowledgement, I send again, send again, send again. Finally, this goes through, and finally the acknowledgement reaches me after some time. This is guaranteed as long as we don't lose every packet in the network, which is a fairly bad situation. Okay, so that's it. That's the simplest thing we can do. Now, these sequence numbers, we need them in order to, even in this simple protocol, we need the sequence numbers to not get confused. And we only need actually two sequence numbers. Normally, I would enumerate all the data units I get above. I would enumerate them 0, 1, 2, 3, etc. Give them sequence numbers when I transmit them. But after a while, I have been counting so many so many data units from above that the number of bits to represent the sequence number becomes prohibitive. So we always need to reuse sequence numbers, and the smallest number of bits we can use for a sequence number is just 1 bit. And that is all what's needed here for stop and wait. So we need two sequence numbers, 0 and 1. So how is this used? Well, the transmitter has a state variable that keeps track of the transmitted packets. And the receiver keeps a state variable that keeps track of the received packets. That's it. And the convention is that the state variable at the transmitter, S last here, which is either 0 or 1, is the sequence number of the last transmitted frame. Okay? And the transmitted frame, information frame, is the data that I get from the layer above, the sequence number, plus maybe some protocol overhead, whatever. I don't know what that could be. And then some error correction code check bits for that. Okay, so this is the basic layout of an information frame. And this is called an information frame because it carries user data. However, to guarantee this in sequence, error-free delivery, we need to have acknowledgements from the other side. And this is called a control frame or acknowledgement frame. It carries no user data per se, but it's needed in order to make the service work. So the receiver maintains this state variable called rNext. And it's the sequence number of the next expected frame. Okay. So at the receiving end, here I'm standing here at the receiver, I'm expecting to get, say, frame 0. Then rNext is 0 for me. When I get frame 0, the next frame I expect to get is 1. So I changed my rNext to 1. Okay. So when I'm standing here getting frame 0, which is good because this is what I expected, it's error-free and everything, I delivered that up to my upper layers, and then I send back an acknowledgement. And in the acknowledgement, I send back my value of rNext, and that is the frame I'm expecting next. Okay. So the frame that's sending back is rNext, the next frame I would like to see, plus some check bits, because here, me being the transmitter, I need to check whether the acknowledgement I get is correct. That could also be an error, could also be lost. So we need to protect that also. Okay, now the receiver, I said, accepts a frame with this sequence number S last if and only if rNext is equal to S last. So here I'm the receiver, I get a packet, I get it from the layer below it. I look at the sequence number here, and if the sequence number says 0 and I'm expecting 1, what do? I throw it away. Okay? If I'm expecting frame number 0 and has sequence number 0 and it's error-free, then everything is good, and I delivered that up. Okay, questions so far? Okay, so the only thing which is a little bit tricky here is the interpretation of S last and rNext. Okay. So S last is the last transmitted packet from the transmitter point of view. rNext is what is expected at the receiving end, not yet received. Okay, so let's look at the timing diagram here to clear up these ideas and see how these state variables when they change value and so forth. One needs to start at the predefined state. Okay, we're not going to talk about exactly how to do this, but we just assume that when we power up things, the receiver puts its rNext to 0, while the transmitter puts its S lost to 1. Okay, so this we could have done it something differently, but this is the starting point. We need to agree upon the starting point. Okay, so what's going to happen here now? The higher layer at the transmitter is going to request a transmission of a data unit, service data unit. So this is then accepted by the ARQ. So I'm in this layer. I get the SDU up here. So I say, okay, I'm going to send that. I update my S last from what it was to what its current value is, which is 0. So the first frame which is transmitted has sequence number 0. Okay, so that's sent over the channel then. So we have here the sequence number 0. And it's this data unit. Okay, so at the receiving end, okay, and we start a timeout also. At the receiving end, we inspect the packet here. We see it's error-free, very good. It has also the right sequence number, 0 and 0. right sequence number, so we accept this, and we deliver that to the upper layer. And now we're going to send an acknowledgement informing the transmitter that this packet has now been delivered. Okay, and before doing that, we switch from the current, the previous expected frame, which we have now received, and now we're expecting frame number 1 next time. And it's actually this number that we transmit back to the transmitter. Okay, so the receiver tells the transmitter, I'd like to have frame number 1. And when the receiver says that, it understands that the receiver has gotten frame 0 because it wants frame number 1 now. Okay, so the acknowledgements for frame number 0 has a request for frame number 1. So these are the same thing. Question?
Will the transceiver send the next package before the timeout, or always wait until the...
Okay, so the question was about timing. When is the transmitter going to send the next packet? And the transmitter waits until it gets an acknowledgement or when the timeout expires. One of these two events.
So it doesn't send it the same rate all the time?
No, no, it waits. Because the time it takes here could be variable. We don't know this before we actually transmit. Okay, so what's going to happen then is that the transmitter sees that, okay, my frame number 0 was successfully delivered, so now I can accept a new data unit from the layer above. Over all this time here, the transmitter is blocking its upper layer. It says, okay, I'm busy, I cannot transmit any more packets now, so please wait. Okay. But now, this transaction has now delivered the service data unit 0, so now the transmitter is ready to do the next packet. Okay? And then it switches its state variable, because over all this time here, it was frame number 0 that was in action, that was, you know, being in the process of being delivered. But now it's time for packet number 1. So we transmit packet number 1 here, which has now sequence number 1, and then the service data unit number 1. It actually fails here. Okay. So what's going to happen? Nothing is going to happen at the receiver here, because the receiver doesn't know that there is a packet coming. And here the timeout expires here. Now the transmitter knows that something has gone wrong and transmits the packet again with the same frame and the same sequence number. This one goes through. Okay, there's a timeout also started. This one goes through and gets delivered. And at the same time, we update R next to the next number, okay, which happens to be 0 in this case. So it goes between 0, 1, 0, 1, 0, 1, 0, 1, etc. And S last here goes from 1, 0, 1, etc. Okay, an acknowledgement is sent back. And if it has R next equals 0, it means that we received frame number 1. I'm requesting frame number 0, which means that I received the previous frame. Okay, and then we continue, and now S last gets gets updated from 1 to 0 here, and now we're transmitting SDU number 2. Okay, and service data unit number 2 gets sequence number 0, right? So this is the global numbering of the data units, only here for illustration. But in the transaction between the protocols, it gets a sequence number, which is either 0 or 1, depending on in which order it comes, right? So one can take this modulo 2 if one like, and then we get the sequence number. Okay, questions on this? So this is fairly important that we get a clear grip on this, because now it's going to get more complicated as we go along. But the main idea is that the transmitter and the receiver maintain state variables in order to get synchronized every now and then, right? And that these state variables changes time at specific events. So R next here changes whenever we deliver a new packet to its upper layer. And S last here changes its number every time we transmit a new packet for the first time. Okay, so S last here is not updated here because we are transmitting still frame with sequence number 1. Okay? All right, so this was the basic operation. That means that we can lose frames on this end here, but we don't lose the acknowledgements. So let's see what happens when we do acknowledgements or when the timeout here is too short, because that's when we had problems before. And so the problems are solved, and I'm just going to briefly mention why this happens. Okay, so one problem we had in the past was that when we delivered a packet like this, the transmission of the information frame goes well, but the acknowledgements get lost. Okay, then the transmitter does not know that the receiver has received this and interpret that as, okay, we need to retransmit this one. Okay, so that's what's happening here. So it retransmits again. But here, look what happens now. The receiver can see, okay, now I'm getting frame number 0 again. I already received frame number 0. I'm expecting frame number 1. So I know this is a bogus retransmission, something that I can ignore. So the receiver ignores this. It has the wrong sequence number. I don't want that frame. I throw it away. And I send an acknowledgement again, reminding that okay, so we can understand that something has gone wrong here. From the receiver's point of view, we know that something has gone wrong here. For instance, maybe the ACK got lost. So I'd retransmit the ACK here. And then the receiver says, okay, now I got an acknowledgement for frame number 0. Probably the transmitter will believe it's this frame that was decoded and not this frame. It doesn't matter though. Right. Still, the SDU 0 is delivered exactly once. Right? And once this has done, the transmitter can then accept a new service data unit and transmit that, etc. Right? So lost ACKs, no problem. How about premature timeouts? Premature timeouts is when we retransmit packets too quickly, that we don't allow for the time it takes for the packet to go over and the ACK to come back, right? So we're a little bit aggressive here. And that could be the case because we don't know how much time it takes really to transmit that packet and get the ACK back. It can vary due to many different reasons. So, and as we will see later on, it's actually beneficial to have the timeout as small as possible, but not too small. Okay? So we don't want that to be very long in the timeout. And the reason for that is that it might take, yeah, we'll see that later. Anyways, so here, the transmitter transmits packet number 0, frame number 0, which is delivered. The timeout hits here. So now the transmitter gets nervous and thinks, okay, so this frame has been lost, so let's try to transmit that once again. But here at the receiver, we inspect the sequence number here, 0, inspect what we look at our state variable and see that they don't match, right? And therefore we ignore that frame. Okay, so this frame is ignored. We transmit the ACK again, and here the ACK actually is received already here at the transmitter side. So now the transmitter knows that frame number 0 has been delivered. Okay, you might believe it's this frame, but it doesn't really matter, even though it was this frame that was delivered. It's the same data content. Okay, so now the receiver is ready to take the next one, and the whole process repeats here. So there will be no duplications here due to premature timeouts. Questions? Yes?
Is it possible for the ACKs to change from 1 to 0?
Yeah, so the question is, can the acts here be changed in transit? Yes, they can, but here we go. We actually protect it with a CRC. So this could be expected, seen at the receiver side, or actually the transmitter side. So if it gets an acknowledgement frame that seems to have errors in it, it ignores it. But that's a good question, right? Okay, so let's go into detail a little bit on how the transmitter and receiver actually works. So the transmitter looks something like this. It starts by initializing its state variable to 1, okay, by definition. And then it goes into what's known as the ready state. So it's ready to receive data from above. Once it gets data from above, a service data unit from the upper layer, it updates its sequence number. Okay, so basically taking the sequence number and modulo 2 added to 1 to it. And then it goes from 0 to 1, 1 to 0. So it toggles between 1 and 0, 1 and 0, 1 and 0 through this operation. Okay, and then it starts a timer, transmits the frame, and it uses the S/, the just updated state variable in its transmission. Right, and then it goes to the wait state. And in the wait state, two things can happen. Or first thing we do when we wait, then we are blocking data from above. So when waiting for the frame to be acknowledged, we don't accept new data from above. So we block the upper layer here. And then two things can happen. Either the timer expires, and then we assume that something has gone wrong, and we reset the timer and retransmit the frame. Or we receive an ACK frame from the other side. Then two things can happen with the ACK frame. Either there are errors in it, or it has the wrong sequence number. Then we ignore it. Wrong sequence number meaning it does not acknowledge the frame that we just transmitted. Okay, that could happen also. If there are no errors and the ACK has the correct sequence number, then we know that things have gone good with the frame that we just transmitted. And then we update. Okay, so here's the check. We look at that R next in the frame that we got is our current S/last modulo 2 added to 1. So if my S/last is 0, meaning that I transmitted frame number 0, I get an ACK back with frame with R next equals 1, then things are good. Okay. If it's 0, then things are bad. Okay, so in that case, if things are good, then we go to the ready state again. Okay, so the receiver, the transmitter, sorry, toggles between then ready and wait. Okay, and switches between these states depending on events that happens. Questions? No? Okay. Receiver is quite simple actually. It starts by initializing R next to 0, meaning that the receiver expects to get a frame 0, the first frame it receives should be frame 0. And then it goes into ready state, which means that it awaits arrival of a frame. So here, if I'm the receiver now, I'm just initializing and then I wait until I get something from below, from the layer below me. Once we get a frame, then it's time to check it for errors. So if no errors are detected, then we look at the sequence number. If the sequence number is the number that I expect to get, that is that the sequence number is equal to R next, then it's a frame in the right order, and then I accept it. So I deliver then, I get the frame up here, I check it for errors, it's error free, then I check for the sequence number. If the sequence number is correct, then I deliver that up, right? Otherwise, I throw it away. Okay, so if the sequence number is not the expected one, then we throw away the frame and we retransmit an ACK saying that, okay, I received something which I was not expecting. Would you please send R next time? If errors are detected, then we don't do anything. We just throw it away. We don't even send an ACK back because we can't trust anything in the frame. Questions? No. Okay, so is this a correct protocol? Also, what do we mean by a correct protocol? A correct protocol is that something that if we execute this, if we code this up, will we make sure that we deliver packets error-free in sequence? Okay, and to prove the correctness of a protocol could be fairly involved. So I'm just going to hand wave my way through this a little bit, and then leave proof of protocols for another course. Okay. But the main idea here is that one would like to look at how these state variables can change, and from that one can deduce that they change in a way which makes sure that we deliver packets in sequence error-free. Okay, so the main idea here is that we have a state at the transmitter, which is slast, one state variable. We have a state variable at the receiver called rnext. These together forms the global state of the transmitter and receiver at the same time. So slast here means that the frame slast has been sent, and rnext means that the receiver is expecting to see a frame with sequence number rnext. Okay, so we have now binary state variables, so we only have 4 possible global states, 0, 0, 0, 1, 1, 1, or 1, 0. Okay, so these are all the possibilities we can be in. And let's start here, okay, because this is where we start using the initialization we had before. The first frame which is received from by the transmitter from its upper layer will make its slast go into 0, and rnext is already 0 by initialization. Okay, so here we transmit the first frame. Okay, and then 2 things can happen. Either it's delivered or it's not. If it's not delivered, then rnext will not be changed, and slast remains to be 0. So we can retransmit, 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 retransmit. Nothing happens to slast or rnext until the frame is delivered. Okay. So when the frame 0 does not arrive error-free, we just cycle through this state. Okay, that's the only thing that can happen. But after a while, frame 0 arrives error-free at the receiver. Okay, and since it's frame 0 and the receiver expects to see a 0, it accepts it. Okay, which means that it updates its rnext from 0 to 1. And we go to state 0, 1. Okay, now we're here. So what happens next in the protocol is that the receiver here just receives the frame it likes, it's the right sequence number and everything like that, and then it sends an ACK back. This ACK is acknowledging frame number 0 because that's what you just received, but that ACK might not be received properly, right? It might get lost, and then the transmitter does not change its state until it gets an acknowledgement for this. So here we can retransmit acknowledgements and keep on doing this forever. We will not change this state until the transmitter receives the ACK. Okay, so when the acknowledgement for frame 0 arrives error-free, then the transmitter updates its sequence number from 0 to 1. So we go from 0 to 1, and then we're in this state. And we're ready when we transmit frame number 1. And then we can cycle here until frame number 1 arrives error-free. When it arrives error-free, the receiver updates its rnext from 1 to 0, and then we're here, and we transmit the ACK until it arrives, and when it arrives, we're up here again. Okay, so I claim that these are the only transitions we can do in this state diagram. There is no way we can go from here to here, or here, back here, or something like that. This is the only thing that could happen. Right? So if we look at what's going on, we can cycle here for a while, and then we pop over here, and then we can cycle here for a while, and then pop down here, cycle here, go over here, cycle here, and go over here. Right? That's the only thing that could happen. But what happens with the frames that we transmit? Well, first we transmit frame number 0, and it arrives error-free. Then we transmit frame number 1, it arrives error-free. Then we transmit frame 0, error-free, frame 1, error-free, and so forth. So we see here, we're doing things in the correct order. Hence, things work. So this protocol is correct. Questions? Crystal clear? I thought it was complicated when I saw this the first time. Yes, question?
I was just wondering with the global state.
Yeah?
Is that to both receiver and transceiver?
Exactly, right. So the global state is the state of the universe. And the universe consists of the transmitter and the receiver in this case.
Why would you want to have a global state when you have two local states?
Yeah, the reason why we introduced the global state is to reason about what could possibly happen here. And we would like to see that if we go along the possible paths here, we cycle between delivering frame 0 and frame 1.
So like you never used the global state?
No, it's only for illustration, right? For executing the protocol, the receiver only has this to work with, and whatever it gets from the receiver in terms of informing I mean, when I'm the transmitter, I send frames with S last as the sequence number. If I'm the receiver, I send back acknowledgements with R next. So these state variables flow back and forth between the transmitter and the receiver. One informs each other of one's local state. And based on that and one's local state, one executes these rules. The rules which we had here, for instance. So here we see what we do with our own state and so forth. Right?
Then the last question.
Hmm?
So the transceiver's variables can only have two different combinations, like 0, 1 or 1, 0.
Exactly.
Yeah, it can never be 0, 0. Except in initiation.
No, it can be 0, 0 for sure. It can be. This only means that the transmitter transmitted a frame called 0, yeah, and the receiver is expecting to get a frame 0.
Yeah, but if the transceiver has 0, then it just transmitted 0.
Exactly.
And if the next one is 0 as well, then it should transmit 0 again?
No. So the question is here, how do we, how the transmitter only transmits frame 0 until it gets an acknowledgement that frame 0 has gone through. Yeah. And then it gets the next frame and then send that one.
Well, that's what I meant.
Mm-hmm.
The transmitter can only have 1, 0, 0, 1, never 1, 1, or 0, 0.
Exactly.
Yeah, is it like that?
I think I understand. If I understand your question correct, the answer to this is yes.
Yeah, so
if I understood your question wrong.
We only have two setups. Like.
Yeah, so let me see if I can decode this. So when we transmit data, a frame, there is only two possible sequence numbers, 0 or 1. Yes. The receiver can only expect either a 0 or a 1 to be received, right? So the global state at any point in time, the global state is whatever we have up here and whatever we have down here. So here the global state is 1, 0. Now it becomes 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, and then 1, 0. So that's how we should read the global state, right? So I hope I answered your question. Yeah. Sort of. Okay, otherwise let's take it in the break. Yeah. But these things are a little bit complicated when seeing it for the first time. So one has to, look at these timing graphs and so forth and do a few examples. And then also, of course, you're going to do this in the project also. So you have all kinds of possibilities to try this out. the stop and wait. So now my PowerPoint crashed. Okay. So now let's do some analysis to figure out whether this protocol is any good in terms of efficiency. Because what we would like to do is to deliver a service, right? So that's what we're trying to do. We're trying to deliver a service to the layer above, which delivers packets in sequence without duplication and without errors. And we do that by using the layer below us. The efficiency of a protocol is a measure on how efficient we are of using our resources. So our resources is the layer below us. So we want to say something about the efficiency of a protocol. And so we're going to do some analysis to figure out that for the stop and wait here. Okay, so. Okay, so we have now a transmitter and we have a receiver. And there is some data that needs to go from the transmitter to the receiver. So there is some, let's call it some type of communication channel line here on which we transmit information frames. So this is data that goes from the transmitter to the receiver. At the same time, we can transmit control frames in the other direction. So these are the acknowledgements and so forth. So here we can transmit control frames. So in particular, the acknowledgements. So we differentiate between data frames or information frames and control frames or ACK frames is the same thing. And this transmission of these two frames can happen at the same time. Okay, so we assume that there is one connection in this direction and one connection in the other direction. So these frames can meet each other in time, right? In time and space. So we assume full duplex transmission. So with the word full duplex, it means that I can transmit data in both directions at the same time. So I don't need to take turns, first this way and that way. Okay. Okay, so now let's draw a timing diagram here. And this, from the perspective of the transmitter, I'm not going to be able to fit this in here, so let's do this up here instead. So this is from the transmitter point of view, and then we have from the receiver's point of view. And at some point in time, the transmitter transmits a frame. Okay? So suppose it starts here, and then the first bit is sent out on the frame at this point. So the first bit is transmitted at this point in time, and the first bit arrives at the receiver at some other time. It takes some time to propagate over the channel. The last bit of the frame is transmitted sometime later. Okay, so here's the last bit, and the time between these two times is called the frame time. The time it takes to transmit a frame. So first bit And here we have last bit. Okay, and the last bit will arrive here at this point in time. Then suppose that this frame was gone through error-free. So after a while, or at this point in time, the receiver, what does it do? Well, it checks the frame for errors. So it checks the CRC or whatever error detection code we have. And suppose everything is good here. And then after some time, some processing time, it starts to transmit the acknowledgement back. And the acknowledgement is typically shorter, fewer bits than the frame. So it's a little bit shorter time to transmit that. But it will arrive at the receiver at this point in time. And then after some time, the transmitter looks at the acknowledgement, checks for errors, and see if everything is good. And at this point in time, is now ready to transmit the next frame. And then that frame goes over like this, and so forth. Okay. So here's the timing diagram. We transmit frames, we transmit acknowledgements. If everything is good, we transmit next frame, acknowledgement, and we go on, so on. Right? Okay. So the time between when the first bit was transmitted to the first bit was received, this is called the propagation time. So let's write that as tprop. And then we had the time it took to transmit one frame, and this was tf. The next thing that happens in the receiver is that there is some processing. Let's call that tpros. And then we transmit the acknowledgement. And the time it takes to transmit the acknowledgement, let's call that tac. And then we have some propagation time again, tprop. And some processing time, tpros. And now we have all the time variables we need in order to describe the time it takes from initiating the transfer of a frame until we're ready to transmit the next frame. And that time is sometimes called the turnaround time or the reaction time. So this time, the time from when the first bit was transmitted until we're ready to transmit the next frame, this is called T0, or reaction time. And to get T0, we simply just add all these time variables together. So T0, we see we need 2 propagation times, 2 processing times, 1 frame time, 1 acknowledgement time. So it's going to be 2 tprop plus tpros plus tf plus tac. Okay, so far, right? Let's take a break now, so 15 minutes.